All right, thank you. Well, I will talk today about exactly this, popping calc with hardware vulnerabilities. I'm super excited to finally share this research. So I started working on this a few months ago, and back then my thought was pretty much regarding hardware vulnerabilities was like, well, this is hard, right? Like, I know there are lots of people working on this. There's these really cool bugs being found, but usually, like, if a bug is found in public, it's dead, right? So also um, for me, this was so far out of my comfort zone. I like software security. I don't like hardware security, so I couldn't contribute anything to this area in any way. Except then something changed my mind, and that something is what I want to tell you about today, and I hope I change your mind as well if you're still on the edge, which is I was able to apply it to a target that I care about. And at the end of this presentation, we will hopefully pop a calculator using only publicly known vulnerabilities, and will still work right now. It's not fixed anywhere. So let me introduce the target. If you Googled my name, you might have figured it out. This is a talk about Chrome. Let me move the mouse. OK. So in the past, I was doing research on the Chrome renderer. So if you're not familiar with how browsers work, Chrome looked pretty much like this, where, well, you have the renderer processes which touch all the untrusted data, like the JavaScript and HTML rendering. So you have a huge attack surface. But so that you can't just pop shells on everyone's machines, there's a sandbox around it, right? But in the past, you didn't really need to escape the sandbox, because as you see in this picture, multiple renderers are in the same sandbox, which means as soon as you exploit one of them on like evilwebsite.com, you can read the cookies from accounts at google.com and do lots of stuff. And since nowadays everything interesting is on the web anyway, who needs to get to the OS level, right? Except then, at some point, Chrome started making changes, and they introduced something called site isolation. And now every renderer is in their own sandbox. And even if you can compromise one of the renderers, the site isolation should still enforce the security guarantees of the web platform to some degree. It's not exactly the same origin policy, but a little bit less than this. It's same site. But in the end, like the renderer exploits became much less valuable for me. And I started looking into what was on my bucket list for a long time, which is trying to find a sandbox escape. And so if you remember the title of the talk, it's been a while, I know, but we will use a hardware bug for this. And maybe if you know a little bit about what hardware bugs are out there, while I explain some details about Chrome, maybe you can figure out at the same time where this is going and what we're going to do. So the first thing you do at this point is, OK, what is the attack surface, right? As you see in this picture, you have a bunch of arrows. The first one is, well, you can attack the kernel. It will be OS-specific, and then, but this is pretty locked down by the sandbox. So on Linux, you have seccomp, which only allows you to do a few syscalls. On Windows, you have the Win32k lockdown, so you can't do any calls to Win32k. So it's kind of limited on what you can do. Also, I want to do Chrome research, not Windows kernel research, so that's not for me. The other thing is the network process, where Ned Williamson, for example, found some cool bugs, and which can be very nice because it can be potentially a one-shot bug that just gives you code execution right away in the network process without going through a render exploit. And the thing I'm more interested in was the attack surface with IPC mechanisms. And this is what we're looking into today. So as you can see here, like the renderer will need some way to talk to the browser. It will need to maybe talk to other renderers, to the network process, to the GPU. Since the renderer itself is in a strict sandbox, it can't do much by itself, right? So there must be lots of functionality implemented outside of the sandbox. And first, some background. So the IPC mechanism in Chrome is called Mojo. There are actually two, but the one is going away and will be dead anytime soon. So Mojo is the one we will talk about today, and most of the stuff is already using this. So let's say I'm in a renderer. I want to do this call from JavaScript, fetch www.google.com. I'm not allowed to talk to the network, so I can't open a socket, right? So I will talk to the network process and using some Mojo IPC call. And then the way this is implemented is, first there's some interface definition language for Mojo, which is very simple. Like you define an interface, and then you have methods, and then the method has options, just like in every other programming language. And then if you look at the Chrome code base, there will be a client implementation and a server implementation of this interface. On the client side, well, it's just a stub that you get somehow. On the server side, you subclass this Mojo URL loader factory, and then you just have to override this create, load, and start method, implement it, somehow magically connect the two with each other through some message pipe, and then you can use, on the client side, you can use the stub and make calls directly to the other process. So there are lots of interfaces that are reachable from inside the sandbox. There are actually like, I think, over 100 different Mojo IPC endpoints that the renderer can talk to. So there's lots of attack surface here. But in particular, there are also the IPC is also used by the browser process itself and by the network process. So there are lots of interfaces as well that the renderer is not allowed to talk to. For example, in this picture, you will see the GPU host, like the renderer will not be allowed to talk to the GPU host. The renderer will not be allowed to talk to the network service. And also interfaces can change behavior based on who is talking to them. So we have here the URL loader, which we know the renderer is allowed to use, but the browser is also using the URL loader. But if the browser is using, the URL loader will not have the same origin policy. So you might wonder, okay, there are multiple interfaces. How does the Mojo actually keep track on what you're allowed to talk to? And then this is documented in the Mojo security docs. So if you read this paragraph, well, the end pretty much summarizes it. There's some kind of secrets that are used for addressing, and if you leak these secrets, so these secrets are called port names, the addresses of an IPC endpoint. If you leak the secret, that means you leak the capability to talk to this endpoint. And you might, at this point, when I read this, I was like, this sounds pretty interesting. Does that mean if you have a info leak in the browser process, you can use that? Like, you don't need a proper memory corruption bug. You can just use it to leak these secrets and talk to arbitrary IPC interfaces? And yes. So as everyone would do in my situation, I decided let's take an old bug and let's write an exploit for this, right? So there's, from Ned Williamson, there was this nice bug in the browser process which was rated as medium back then. And I thought, like, this would be a cool example to try it out. So it's in the blobs. If you're not aware what blobs are, it's like this web API that allows you to store data. It stands for binary large objects. And if you look at this code, this is the patch. You will quickly see this is just an integer overflow, right? Like, this is a very simple bug. And let's exploit this quickly because it's super, super easy. So blobs come in three types. They either are backed by data, by a file, or the third one can be a reference to another blob. And this is exactly where the integer overflow happens. So all you need to do to exploit this is you create one blob with some data. So you and the renderer, you tell the browser, hey, create a blob, here a bunch of A's. Then again, you tell the renderer, you tell the browser process, hey, can you create another blob? By the way, this one references the first blob. Also, the offset is -1000. And then you read from it, and the browser will just give you like 100 megabyte of heap memory or whatever you ask for, as long as it doesn't crash, of course. So now, this heap memory will have these secrets we're interested in, right? The secret port names used for addressing in the Mojo IPC. So the idea for the exploit is now, well, let's just grab them and send messages to IPC endpoints we're not allowed to talk to. For this, we first need to figure out what do they actually look like in memory. How do we notice if something is a port name or not? And this is actually very simple to do because a port looks like this. Like, you have a node name and a port name. Both of those are 128-bit random values. You will know the node name usually because the node names are, like, there are not so many nodes. Like, the renderer, the browser, and the network process, for example, are interesting. And you will already have connections to them, so you already know the name. So you can just search through the heap, through your heap dump from the browser find the node name. If there's 128-bit of random-looking data behind it, that's probably a port name, and you can use it and send messages to some interface. But at this point, what interface can we actually talk to, right? Like, because there's no, hey, spawn a shell, run this command interface, because that would be stupid. So I went to my favorite hacking tool, which is called Code Search. And you see the query there. I'm searching for all the Mojo interface definition language files, and look where if one of them is using file paths. With the idea, well, if it uses a file path, if you pass a file path on an IPC interface, it's probably a trusted connection, and the other side will probably do something with it, like either read from it or write to it. And both of that is probably bad if you can control what the path is, right? And then one of the first things you find is, well, the URL loader again. The URL loader, and this is in a code path that you can't trigger from a renderer. So this is like in a privileged code path from the URL loader. And in particular, this one, so this can only be triggered if you're coming from a connection from the browser process, which we would be able to spoof, right? And in this case, this pretty much says this path is used for file uploads. So if I come from the renderer and I say, hey, upload etc+wd to evil.com, the network process will say no. But if you come from the browser and say, like, upload etc+wd to evil.com, the network process will be like, sure, sounds good. And that's the whole exploit. In summary, like, well, first get code execution in the renderer. So just use a 0-day of your choice. Then you trigger a bug that gives you heap data from the browser process. You find the privileged URL loader factory port name, and then you inject messages telling it, hey, upload this file, and you're done. You can read arbitrary files from the machine. And this works on pretty much all OSs. So maybe you figured out already where this is going, because we're going to talk about hardware bugs, right? And if I think of hardware bugs, like, there are a bunch of, like, besides Rowhammer, most of them just give you info leaks. But this is exactly what we need to trigger this, right? Like, if we have an info leak that gives us memory from cross processes, we could potentially use this to just read a port name from the browser process without ever having an actual bug in the software, right? So at that point, I came back to my original point of, well, hardware bugs are hard, but maybe I should start reading the papers. So I looked them up, and, well, there's Spectre and Meltdown, which I think everyone heard about. And then there's Rambleed, Plunder Vault, MDS attacks, Zombie Load. I should have memorized this. I think that's the Blueforce logo. Cash Out, which is pretty recent, and, well, plenty more. And a quick note, if you found a hardware bug and it's not on this list, it's because you don't have a logo, and you should really have a logo for your bugs. Everyone knows it's not a real vulnerability without a logo. So the one bug, like one of the list, MDS attacks, and in particular Riddle, caught my eye, because when I started reading all these papers, this one just said, well, leak information across address space. This is in the abstract. So I actually did read all the papers, not just the abstracts. But this one was like super promising. OK, cool. This is exactly what we want. But it has been public since May 2019 already, right? And this is like late 2019. So I'm like, OK, well, this is probably be fixed already. So I Googled like exploit Riddle, how to. I find a POC. I try it out. It doesn't work on my machine. I'm like, OK, it has been fixed. I read the documentation about it. Everyone says it's been mitigated. But except if you should also disable hyperthreading to really mitigate it. I was not really sure what that meant. So I was like, OK, but I really want to try it out. So I downgraded my microcode on my machine because it was fixed with a microcode update. I run the proof of concept that I found again, and it still didn't leak. So I started like re-implementing stuff myself, changing stuff around, changing like what kind of victim process you use to actually leak memory from. And at some point, it started leaking, right? I was like, OK, this is cool. Let's reboot the machine, reapply the microcode update, run it again, and it's still leaking. And that is weird. Probably something with my microcode update failed, right? So I run the same thing on my other computer, on my laptop, and it still works. And like, okay, this is cool. Maybe this note about hyperthreading needs to be disabled is actually quite important. So, yes. So let's write an exploit for this to let's try to write an exploit for this, right? And like try to use this to leak these port names. But first, since this is the main point of this talk, let me quickly explain to you how I think the exploit works. I'm not 100% sure. If someone knows better, please don't tell anyone. So this is how I learned about CPUs in university, right? There's some front end, then there's some execution unit, and then caches, and somehow like if you want to execute instruction, it gets decoded, then it goes to the execution unit. Like depending on what instruction it is, it will load memory, and then it will go to the cache and like read the memory for you. Except with Spectre, everyone learned this is not what CPUs do. They speculate. So they have some kind of queue where instruction gets queued up, and then if you need to wait for a memory load, that is pretty slow, so you just continue executing stuff. And if there's a branch, you just guess which way it will go. Well, yeah, you make an educated guess. And at some point, so the trick is you don't make the changes visible. Just after a while, when you notice, OK, all my guesses were right, then you make the changes visible, and the CPU, like you retire the instructions, it's called. So you update the architectural state of the CPU. So then I learned, well, there are also these buffers in between the L1 cache and the L2 cache, and after the load port and also after the store port. But that should be a good enough model for us now. So let's say I have a privileged process that tries to read a secret. It will first go through the fetch and decode in the front end. It will see, OK, there's a memory load, so it goes to the load port of the execution unit. It will not see the value we're looking for in any of the buffers or the caches. So it will just load it one by one everywhere and return it to the architectural state, to the program, right? So now assume there's a context switch happening, and now an attacker process is running. And the attacker process does the same thing. It fetches and decodes some instruction. It tries to load some memory. And then something goes wrong, meaning there's an exception or something. For example, if you read from a null page, right, it will trigger seg fault, there's an exception, everything breaks, and the CPU is like, well, I need to do something, right? So I need to, but I'm not the one handling the exception, so I will just return some data that I have lying around here and just give you this thing, because we're in speculation, right? Like we will at some point figure out this was wrong and just never make the change visible. Except that we also learned with Spectre, well, and before that, actually, the papers before that. But we also learned you can leak from speculation. So because speculation has side effects that you can observe, usually, for example, if you access memory, the memory gets loaded to the cache, right? Even if that happens during speculation. So afterwards, if some memory got cached, afterwards, you can just try to access memory. And if the access was fast, you know it got cached during speculation. If the access is slow, you know it didn't get cached during speculation. So the usual attack is flush and reload, it's called, where you just make an array with 256 pages, and then you use a secret byte, use it as an index to access this array at some address, at some offset, and that's it. And then after speculation, you just go through the whole array. If you see one of them is really fast to access, you know, OK, this is the secret index that you just leaked from speculation. But that got fixed. So now with the microcode update, I believe, like just on the context switch, all these buffers are flushed, so you can't really leak from them anymore, except that this is still not how CPUs look like. Nowadays, with hyperthreading, it looks more like this, where you have two front ends. So even flushing these buffers in between a context switch doesn't help, because you can just run your exploit at the same time as your victim process. OK, so far so good. The exploit is super simple. So this is a proof of concept from Pietro Borello, which is public for a while, like just a month or so after the paper got released. And it's really like, so if you're not familiar with Intel TSX, this xbegin instruction will pretty much just catch any seg faults happening and restore the state to the xbegin and then go into the else block. And all this is doing here is it's accessing mapping, which is null, so it will seg fault. But during speculation, it will use the secret value leaked from there as an index to the mem array, and recover will do the flush and reload, and that's all there is to it. So it's super simple. So at this point, I will start my demo, because it takes a little bit. I want to say I'm really worried about this demo. I ran it 15 times in preparation. It failed exactly once, which was when I tried to live demo it last time. So, fingers crossed. Anyway, so what is this doing? So this is just a patched renderer. I didn't use a 0-day because that would be irresponsible. It's just a patched renderer. I didn't change the browser code, so this is trying to do a sandbox escape based on this bug. So a few things that we need from here to make this reliable enough and fast enough to work in a real-world scenario and work in a live demo on stage. First thing is we want to optimize the exploit and make it as fast as possible, right? So, well, I wish I had really cool tricks here, but in the end, all of this boils down to you saw this the instruction that leaks the secret value is the one that triggers the seg fault, right? And then afterwards, you go through this huge array and check if you leaked something. But you very rarely leak something. So it's much better to just try to improve the time you spend on actually leaking and reduce the time you spend on looking if you leaked something. So in the end, what I did was like, well, just add a for loop around the leak. Suddenly, the exploit becomes much faster. Or this is the instructions I initially used for timing the access. Like if you want to check if something got cached, well, you Google how to do this, then you find some Intel paper that explains to you, well, just put these instructions. There's a CPU ID that blocks speculation, a memory fence, then you read the timestamp counter, and then you do the same in reverse, and whatever, and then you can time what's happening between these two instructions, right? Except that we don't actually need this good timing, and CPU ID and mfence is really slow, so let's just get rid of this. It will still work, as long as you leave one mfence to block the CPU to just speculating over the next one and breaking your exploit. And then another thing that I had a hard time figuring out, but it's documented everywhere, so if you know what you're doing, you probably have a much easier time, is the CPU is doing stuff like prefetching. So I noticed, like, the smaller I make the probe array, the faster it will be, which I believe is probably because I used less TLB indexes, less TLB entries. But also, if I make it too small, suddenly nothing works anymore, and it just leaks any random value, and just leaks pretty much every value. It tells me every value got leaked, which seems wrong. And this is something because the CPU tries to prefetch. The CPU notices a pattern in your memory access. It starts prefetching things. And then once you actually try to access the next one, it will be super fast because it has already been prefetched. So one simple trick we came up with to just get rid of all this complexity is let's just leak one bit at a time, right? Why do a whole byte? Let's just leak one bit. You don't have to worry about anything. And in practice, it was surprisingly just as fast as leaking bytes, but I'm not entirely sure why. Probably because you also don't need to look at 256 indexes, but now you only need to look at two indexes in your probe array to figure out if you have a bit leak or not. So now we leak from one process. This allows us to leak memory, but we don't control what we leak. We leak random stuff that the other process is accessing. So in order to improve our chances that this is the secret that we care about, we want to make the browser process actually use the secret. So first of all, we're looking at the URL loader factory again, right? That was our target from before. So you can probably trigger an access from the browser to the privileged URL loader factory somehow, but then we'll probably make a network request. This will be slow. So, but you will notice, like, if you look at the network context, if you can leak a connection to the network context allows you to create new URL loader factories, which is exactly what we can just create our own privileged URL loader factory if you can leak that one, Similarly, with the network service, we can create a new network context. If we leak a connection to the service manager, you get the idea. Except that the last one doesn't work anymore. In the middle of me writing the exploit to target the service manager, they changed that. So now I'm going for the network service again instead in my final exploit. So now, the way how do you trigger a connection from the browser to the network service? Well, you look through the network service interface, and then you see this method on peer-to-peer connection count change, which sounds like something we could control, right? Like peer-to-peer connection sounds like something happening in the renderer. So if we tell the browser, hey, this connection count changed, maybe it will forward it to the network service. And this is exactly what's happening. So we have this. So we create a WebRTC connection, and then we have this call update peer connection where we can say, well, this one just connected, or this one just disconnected. And every time you send such a message, the browser process will talk to the network process saying, hey, the connection count changed between 0 and 1. This didn't work. Let me just retry it. Oh, well, it's still running. Anyway. And on every of these, the browser will use some secret, and by from one of the other renderers, rerun the MDS attack, like rerun the riddle exploit, and at some point, we should be able to leak it from the other process and then use it to inject messages. Then one more thing is missing. So I told you we're just leaking a single bit, right? So how do you know which bit it is? How do you stitch these together? And this you can find in the riddle paper already. It's already described in there, which is pretty much you do a prefix matching, or you can also do a suffix matching. So you just GDB attach to the browser, figure out what is in front of the secret. For example, in this case, in front of the secret in red, we have this constant. And then you access it so that just a single byte, or in our case, a single bit, is secret, and the other one is known, and then you just filter on, well, if the prefix was this, then leak the next byte, or leak the next bit, and that's pretty much it. So, except for we're talking the whole time about reading files, but if you paid attention, the title says popping calc. Otherwise, yeah, it would not be fun. So back to the drawing board. Favorite hacking tool, code search, same query as before. Let's find all the other interfaces where file paths are used. And the network context, what a coincidence. If you create a network context, you can tell the network process where you want to store cookies. And the cookies, this will be a SQLite 3 database. So you don't control the file itself. You can just, what this gives you is, you can write a SQLite 3 database to any location on the machine, and you kind of control the content, as in you can insert cookies. And I really hope this worked. Yes, okay. So, first try. So, at first this seemed like, well, this is kind of useless primitive. I don't really know what to do with this. But then there's this startup folder, right? And here in the startup folder of the machine, of the user, you see there's this auto-exec bat, which usually shouldn't be in there. And what happens, I don't know if you're familiar with the bat interpreter on Windows, but to my surprise, it's pretty lenient on what it accepts as in the format. So let's try to see what happens if you give it a SQLite 3 database with cookies. Okay, okay. Okay, so what happened there? Well, it's just this. You insert this cookie, new line, calc.exe, new line, and if you looked at the output, I removed it quickly, but it pretty much says SQLite 3, I don't know what that means, let me ignore this command. Oh, calc.exe, let's execute this. This sounds great. I don't care about all the null bytes in between. Yes, so in summary, I was surprised that this works. All of this is public already. I didn't tell you any secrets here. And still, you can do kind of cool things with this. And I really well, I didn't expect that hardware bugs would be this cool in practice. I hope I could convince you. And I came into this with zero experience on hardware. I still don't know anything. If I hear people talk about it, I always wonder what they mean. And still, I was able to write an exploit like this. So maybe disable hyperthreading. And I think a system, just think of other places where memory, like if you don't have any memory protections between processes, that is pretty bad. And there are probably much more cool things you can do with this. Thank you.